Alright, so we're going to look at August 2020, number 8. This problem asks us to construct a meromorphic function f of z with a 0 at z equals -1 and simple poles at all the natural numbers with residue 1. So the main tool here is the Mittag-Leffler theorem. So let's just kind of read through this. So we're going to let b sub k be a sequence of distinct points in the complex plane having no accumulation point. Okay, no accumulation point. This is important. Furthermore, the Mittag-Leffler theorem requires the sequence of polynomials in the variable z. So that's what these p sub k's are. All right, we've got an infinite sequence of polynomials all in the variable z. And the big deal with these polynomials is that they do not have a constant term. All right. So if we have this sequence of complex numbers and this corresponding sequence of polynomials, then the Mittag-Leffler theorem tells us that there exists a meromorphic function, we'll call it f of z, that has this exact singular part, all right? So the exact singular part is the polynomial applied to 1 over z minus b sub k, where b sub k is that location or that point in the complex plane. So really here, right, this is basically allowing us to place singularities, construct a function with singularities placed exactly where we want them at a countable set of distinct points that don't have an accumulation point in the complex plane. And furthermore, this meromorphic function actually has no other singularities outside of this singular part right here. Okay. So we're going to try and use this for our problem. Okay. So let's start the proof. So first I want to notice, right, that the locations that we want our poles for our function are the natural numbers, all right? This is just the enumeration of the natural numbers. And notice, right, that this is a sequence of distinct points with no accumulation point in the finite complex plane. So far, so good, right? So far, so good. We have our, what was in the theorem statement, these natural numbers are b sub k's, okay? So the next thing in the theorem requires the sequence of polynomials without constant term. So let's instantiate that. I'll say, let's go ahead and consider a sequence of polynomials. Let's call it p sub n of z, where n runs from 1 to infinity, defined by p sub n of z is equal to z, all right, for all the natural numbers. So for every index value, this is the case, all right? So really, every term of this sequence is the same, and they're all just identity maps. And notice here, right, that this has no constant term, all right? Great, so we have a sequence of natural numbers. This is the sequence of distinct points with no accumulation point on the finite complex plane. And we have a sequence of polynomials in z with no constant term. So now, all right, we can go ahead and apply Mittag-Leffler. Now Mittag-Leffler guarantees that there exists let's write this out fully, exists a meromorphic function f of z with singular part p sub n of 1 over z minus n, and since, right, these polynomials p sub n are just the identity map, this is actually just 1 over z minus n, and this applies, right, for all the locations, so for all n in the natural numbers. So this is really good news, right? This is really good news because what is true about this? Well, this factor right here, for this factor, right, it is exactly the case that n is a simple pole with residue 1, right? And you can check that very easily. Residue 1. Okay. So what we've done here, right, is we've guaranteed the existence of a function that at least has the prescribed singularities with the prescribed residues that we would like. So this is a good starting point. Unfortunately, right, Mittag-Leffler is an existence theorem, but, and we want a particular function, right? Luckily though, Mittag-Leffler, the proof of that theorem is actually constructive. So what we can do is we can just follow the proof of Mittag-Leffler to actually construct this function that we've just proved exists. Okay. So given that a factor of this form, 1 over z minus n, has a simple pole at z equals n with residue 1, kind of the naive, right, idea is to consider, right, this series, which is just n equals 1 to infinity of 1 over z minus n. And why is this the naive idea? Well, each of these factors, right, has a simple pole at z equals n of residue 1, right? So if we just add up all of them from n equals 1 to infinity, this, I'll write this out fully, if this series converged, right, if this converged, then it would be a meromorphic function with simple poles at z equals n of, and that's for all n in the natural numbers, for all n in the natural numbers with residues all equal to 1. Okay, right, so this right here would be basically exactly what we're looking for if it converged. But that's kind of the most important part here, because does the series converge? No, it does not. So I'd say here, this series does not converge, okay? So the idea here, in light of this series not converging, the idea here is let's fix this series, let's fix the issue, right, by deleting some strategic selection of terms, right? So what I'm saying here is there are some terms in the series that are causing it to diverge, right? We need to figure out some way to identify what the issue is, right? What's causing this to diverge. and just get rid of them. And we need to get rid of them in such a way that we preserve the desired property, which is that this is a function with simple poles at z equals n for all natural numbers, and every single one of those poles has a residue equal to 1. Okay? So it's not super clear how one might do this, but the trick ends up being the following observation. So notice that this piece, 1 over z minus n, can be written as a geometric series. And this is kind of the key insight here. So let's do that on the next page. All right. So 1 over z minus n is the same as 1 over negative n plus z. Now let's factor out a negative n in the denominator. So now we have 1 over negative n times 1 minus z over n. It's starting to look a little better. Now that's equal to negative 1 over n, and now we have our geometric series, right? This runs from n equals 0 to infinity of z over n to the n. And then let's expand the first couple terms. So this is negative 1 over n, 1 plus z over n plus z squared over n squared plus z cubed over n cubed plus ... right? And then let's do one more iteration of this. So we'll go ahead and distribute that negative 1 over n. We have negative 1 over n minus z over n squared minus z squared over n cubed, and then minus z cubed over n to the fourth minus ... Okay, wonderful. So now let's return to the series that we were trying to fix, right? So remember, we wanted to fix this series here, n equals 1 to infinity, 1 over z minus n. And what I've just done here, right, I've just written the term that we're summing up as a series itself, right, as a series itself. Right? So in some sense, what we can do to identify the terms that are messing with this goal series convergence, what's messing with the convergence here, is I can look at the summations of each of these terms, right? Imagine summing these up. Because that's really what's going on, right? So if we look at each of these terms, right, which of these are converging and which are diverging? Which converge and which diverge? Well, I can tell you, right? So these ones, all these converge. They're p-series, right? The power of n down here, we got n squared and n cubed and n to the fourth. Those are all convergent, and they're convergent everywhere. But what's going on here, this one, this is divergent. This is divergent. Right, it's the harmonic series. So this is our issue. We've identified sort of the underlying cause of this series diverging. So what can we do to fix it, at least theoretically, right? So let's consider, right? Consider the modified series that is 1 over z minus n plus 1 over n. So why did I add a 1 over n again? Well, right, I'm adding a 1 over n to every single one of these terms in the summation. So what that's doing, if we were to expand it out, is in every term, it's killing this, right? It's killing the piece that is diverging. So technically, or at least theoretically, this should now converge. Now, of course, we're going to actually go ahead and check that rigorously, but I just want to build some intuition here. All right. So I want to first just note that we can actually rewrite this. Let's rewrite it like this. This is n equals 1 to infinity. If we combine these terms, we have a z over n times a z minus n. Okay. Now I'll let you do this yourself, but you can also check, right? Check that this has simple poles at z equals n for all n in the natural numbers and all with residue 1. So basically this modification that we didn't actually change the singularities or the residues. And you can check that fairly easy with a direct calculation. All right? So what do we need to do next? All right? Well, we need to show that this series, n equals 1 to infinity, z over n times z minus n, is meromorphic, right? It's meromorphic with really just meromorphic, right? Because I'm going to let you show that it has all the simple poles at z equals n for all n in the natural numbers with the residue 1. So really all I just need to show is that this does in fact converge outside of those singularities, all right? So the strategy here is going to basically be to split this series, right? We're going to split it. And here, let's go ahead and do this. So what I'm going to do is I'm going to fix a radius value. Fix r greater than 0, all right? And I want to split the series like this. Split the series as, right, sum n equals 1 to infinity, z over n times z minus n is going to be equal to the sum, all right? I'm going to say n less than or equal to 2r, where r is this radius, all right, of z over n times z minus n, plus, all right, what would the other term have to be? Well, it would have to be the index values n greater than 2r, strictly greater than 2r, z over n times z minus n. So what's the idea here? Well, given this radius r greater than 0 and this series split, I want to look at the behavior of the series for z in the closed disk of radius r about the origin, okay? So I'm fixing this arbitrary radius value and I'm examining our desired series for z inside the disk at that radius value, all right? So what I'm hoping to find, right, is that this series here is meromorphic on this disk. Because if that's the case, right, if that's the case, what can I do? Well, I can send r to infinity, right, and the argument's going to hold. And then I'm going to have a meromorphic function on the entire complex plane as desired. So let's do this, all right? So let's kind of examine each of these pieces one by one. So let me grab this. We'll copy it down here. Okay, let's look at this piece first. So notice, right, that n, right, n is less than a finite value. R is a finite value bigger than 0, all right? So this actually has a finite number of terms, okay? This has a finite number of terms, and as such, right, having a finite number of terms, it definitely converges, right? It definitely converges. This is just a function, right? And moreover, it has a finite number of simple poles. And where are they at? Well, they're at z equals n. All right. For n in the natural numbers and n less than or equal to 2r. Yeah? That's exactly what's going on here. So this piece basically is behaving exactly how we'd like it to, right? It's assigning singularities at each n in the natural numbers, and it's giving us the correct residue, and all these singularities are poles. So what we're hoping, right, what we're hoping now is we hope this piece is analytic on the closed unit disk, right? So for z inside the closed disk of radius r, right? We don't care what's happening outside that disk yet, right? We're trying to make an argument about z's specifically in this closed disk, and then we're just going to send r to infinity. So don't worry about any z's outside the disk. So we want to show this, right? We want to show this right here, that this piece of the series is analytic on the disk. So let's see if we can do that. All right. Okay. So in order to do this, we're going to go ahead and use the Weierstrass M test. So let's go ahead and do that here. So we're looking at the series n strictly greater than 2r, z over n times z minus n. We want to show this is analytic in the closed disk about the origin of radius r using Weierstrass M. So what does the Weierstrass M test ask us for? Well, it asks us to bound the absolute value of this series above by something that is convergent. All right, that's all we got to do. So let's look at this series in absolute value. N is strictly greater than 2r. So we've got the absolute value of z over n times z minus n. Let me put absolute value bars around these. So first look at the numerator, and let's draw ourselves a little picture just to have an aid. So here's our complex plane. Let's say this is r. Okay, so z lives inside this circle, and then let's say 2r is out here. All right. So the n values live out here. The n's are out here that we're considering, and the z's are in here. All right. So since z lives in this disk, we know that we can bound this like the following. The absolute value of z is going to be less than or equal to r. So we have r over n times z minus n. All right. And then I want to look at this term, the absolute value of z minus n. And right, I want another upper bound. So I want to actually shrink the denominator. So I actually claim that this is greater than or equal to n over 2. So let's go ahead and see why that is. So let's look at the min value that we could possibly have for the absolute value of z minus n, and we'll kind of use our picture as a guide, right? So n is strictly greater than 2r. So as a visual aid, right, that would be kind of the smallest n we could have. And the closest z in the circle to that would be the one that lies right here. Okay? So we would have, right, this is distance r. And then this distance right here is going to be, right, n minus 2r. Okay? So I'll say that this is definitely greater than r plus n minus 2r, right? So then that's equal to that's equal to n minus r. And then, right, remember that we're considering n's greater than 2r, okay? So what does that mean? Well, it means that n over 2 is greater than r. So what we can do is we can say that this is definitely bigger than n minus n over 2. And why is that? Because n over 2 is bigger than r, so we're subtracting off more. So then this is equal to n over 2. All right, so n over 2 is actually strictly less than absolute value of z minus n as desired. So then we can rewrite this as n greater than 2r. We have r, and then we have n times n over 2, which is equal to n greater than 2r of 2r over n squared. Great. So what's true about this? Well, this is a convergent p-series. Okay. So then by Weierstrass M, we know that this n greater than 2r, z over n times z minus n, basically converges uniformly in the closed unit disk. So for z in the closed, not the closed unit disk, the closed disk of radius r about 0, right? So the series is analytic on this domain, which is exactly what we wanted, right? Exactly what we wanted. So then, right, overall, we find that the series, the original series that we were looking at, that we split, right, that we split along this radius value, it was z over n times z minus n, is, right, meromorphic in the closed disk about the origin of radius r for any r greater than 0, right? So let r go to infinity, right? And we find that this series here, and I'm actually gonna name it now, because now we know it's actually a function, right? That it's actually a function on the whole complex plane. So I'll call it g of z equals sum n equals 1 to infinity z over n times z minus n is a meromorphic function on the entire complex plane with simple poles at z equals n for all n in the natural numbers, and each of these poles has residue 1. Okay, so we're almost there, right? We're almost there. G of z is almost the desired constructed function, but recall that we also want that f of z, which is the function we were trying to construct in the problem statement, satisfy, I believe it was f of negative 1 equal to 0. Yeah. So in other words, all we need to do here is just basically add some constant to g. We just need to add some constant to g such that this is true. So let's go ahead and see what g of negative 1 is. So g of negative 1 is going to be the sum n equals 1 to infinity of negative 1 over n times the negative 1 minus n. And we can actually rewrite this as n equals 1 to infinity 1 over n minus 1 over n plus 1. And the cool thing about this is this is telescoping. So we can actually get a nice closed form valuation for this. This is 1 minus the limit as n goes to infinity of 1 over n plus 1, which is just equal to 1. Okay, so g of negative 1 is 1. Okay, so we just need to add negative 1 to g of z to get 0. Sorry, not to g of z, to g of negative 1 to get 0. So then the function f of z, which is just negative 1 plus g of z, is the desired function. All right, and that wraps it up.